innovative idea or thought.
Good afternoon and welcome to the Silicon Valley Fourth Interest Group. Both of you's classes of individuals here physically present and out there on the interwebs. We've got a full schedule this afternoon of really excellent speakers. So why am I standing in front of you blathering? I guess, you know, it's vindictiveness on my part. I wanted to say, I heard on the radio this morning that there are a lot of people on the East Coast sitting in a blizzard in their cars with no food or water. So why are you in a car in a place where you might get trapped in the snow with no food, water, or shovel?
Adventure.
I guess IQ test failure or Darwin in action or something. I don't know. It seems like, what was it, 79? Big Boston blizzard. It was a combination of hurricane force, storm, and snow, and people were on the highway, and you'd think they'd learn by now. So we got good sound, Dennis?
Just sent email, so
Okay.
I'm catching up with you.
All right, I'm glad to hear it.
Yes,
That may be why I'm standing up here blathering. I wanted to welcome Andreas Wagner from the East Coast, who's now migrated. Do you want to say a few words about yourself? Just to... Here, put this on. Don't hold it. Clip it to your jacket. Stand up in front of there. Stick that in your pocket. Try to lift your East Coast. Try to lift us. You really are quick. That's me.
I gotta clip it on somehow. You can see the static. Does it work now? Mic test. So I'm from the East Coast and not in the Matrix right now. And I started the New England Fourth Interest Group, but now I'm here where we have a bigger Fourth Interest Group. And thank you for having it, for everything. And yeah. All right. Any questions?
Split to go pee. So is the other Fourth Interest Group going to continue?
Yes, I found a new president for or president is strong word, but for me and him. But we have a new president, and he will be continuing the New England Fourth Interest Group, continuing to facilitate it. And that's great because it was going strong and had it was a lot of fun and all that. So it's great that it'll continue in my absence. And
are they considering, you might want to repeat the question because they can't hear me. Are they considering webcasting their meetings?
That's are they considering webcasting the meetings? That's an excellent idea because there were some interesting talks at these meetings. So that's a great idea. I should suggest that to the new facilitator because there were some interesting things that should have been recorded, but were not. So I should. Any more questions? Any questions?
Welcome.
Thank you.
So when's your first presentation going to be?
That I could recycle. So
I wouldn't mind that at all. We'd be grateful for that. You know my email address. You can send me something, and that applies to any of you out in the interwebs. If you've got something interesting that you'd like to present, send me an email. If you can't figure out what my email address is, then really you're not smart enough to talk to us. Anyway, as I was saying, we're more than pleased to entertain remote presentations on any day other than fourth day, or on fourth day if you're talking about the green arrays chip in the afternoon session. Remote presentations have worked out pretty well for that. So without further ado, James looks like he's here and he's ready to go. He's just pointed in the wrong direction. That way.
Oh, right.
That's a screensaver.
Like a random number test.
Okay.
No, not very random.
Small, but he's
No, infinity goes into it. Okay, can everybody hear me? Okay, so as usual, I'm doing my slides on a fourth machine, but these are the fourthiest slides ever, because the last time I came up here, a fourth machine was running the slides, but they were just images that had been created offline by something else. So not very fourthy at all as far as the actual pixels. But here for the first time, I have an FPGA board running a fourth CPU, a J1, and it is connected to an embedded GPU, and the fourth machine is running swap fourth, and which is just a standard ANS fourth, and it's running the slides by talking to the GPU, so that everything is being rendered in fourth. They get loaded off SD card, and there we go. So they're all text, of course, because it's not especially ambitious, but we're fourth all the way down now, so down to the hardware. And the actual GPU is generating 1024 by 768 video, so on the VGA port. So it's a step up. So I had a mini project in mind last month, which was to build an Intel 8080 emulator. The Intel 8080 was, as it happens, my first ever CPU when I was a those were good times, and it was a while back. And it's not especially useful, but it was kind of an interesting exercise. And just fill everybody in on how it all began. So Intel had this magnificent progression of chips. They started with the 4004, which is arguably the first microprocessor, followed it up with the 8008, which was twice as wide. It's a byte-wide machine. 8080 has a lot in common with the 8008, except it was the first machine with stacks in with a stack in memory. It was its big thing. Instead of having an on-chip stack, which was like 7 deep or something, then the 8080 was an in-memory stack. And then the 8086 came, and the rest is history. This sort of became what we think of as the PC. And it kind of looks like Intel was on this fantastic procession of chips, and it was just this unstoppable sequence. But in fact, the 4004 was supposed to be a pocket calculator chip, and it had BCD support. BCD is decimal arithmetic, where you pair up the nibbles in a binary word and treat each as a decimal digit. And it has decimal instructions because it's a pocket calculator chip. 8008 was supposed to, that didn't work out really well for them. So the 8008 was a sort of desperate attempt to take the same core and then use it as a communications controller for terminals. So they added in parity support. So it had hardware parity generation. And that didn't really work out. The 8080 was sort of the last attempt. Tried to soup it up a bit and put outside memory interface on it for 64K. And then almost by accident, people realized it's a computer. Like it can run arbitrary programs. And suddenly this idea that you could take this microprocessor chip and actually run real programs on it of unlimited size. And people, Dr. Dobbs' journal, for example, got BASIC running on it, and suddenly this process begins of people actually making it do something which isn't a specific task, which isn't being a pocket calculator or a terminal controller, but just computing. So it didn't really happen as in an Intel roadmap, it was just accidents until finally things started taking off. 8080 is, for an Intel architecture, quite elegant, which isn't saying something you can say very often about Intel's chips, but it's before things turned into an amazing mess. And it's pretty simple. They've got it's an accumulator machine. All of these are byte registers, and they've got 7 of them. A is the main accumulator. There's B, C, D, and E, and then H and L, which might not make sense, but H and L is high and low. And a lot of operations can work on those. So you get, if you're willing to work in bytes, you get 7 registers. Or if you want to use 16-bit quantities, you can use these 3 register pairs. It is straightforward. It uses just, every instruction is a byte. And the fields in the instruction there, this is a move instruction. So the high bit is 0, the next bit is 1. And then those middle 3 bits give you the destination as a 3-bit field, and the bottom bits give you the source. And then this is the direction of all the moves. So there's 64 instructions, obviously, and depending on what those source and destination fields are, it tells you whether it's registers B, C, D, E, or H or L. So it's simple stuff. And you can sort of see why when the 8080 came around in the sort of mid-70s, people got quite attached to octal again, because the octal digits actually line up. So when you're looking at an octal memory dump, if you're an 8080 owner, then it's pretty handy, because after a while you can just sight read the instructions and you don't need a disassembler or anything. You can just look at octal digits and you'd know that 4 means H, for example. Good times.
Is that this number here?
Right, that's the one wrinkle in this, is that this is a CISC machine, and when you have a source of memory, it actually uses HL, which is the 16-bit register pair, as the memory contents. So it's pretty fancy. You can add memory to the accumulator in one instruction. These were the days of CISC, when these days you'd have to fetch the memory and there's load store instructions. But with this one, you sort of had implicit memory access as if it's another register. Amazing stuff. Similarly, this is another chunk. This is another quarter of the byte instruction set space. With this one, it's ALU operations, the things that modify the accumulator. Everything just sources from some register or memory, just like before, and then does something to the accumulator. Addition, add with carry, subtract, etc., etc. And you can see again that the low 3 bits are the source, the register source, and then the middle thing actually tells you what the instruction is. And that's those two, the moves and this ALU group, that's half of the byte instruction is already taken. So there's another a few sections in the instruction set that I won't go through, but they're all miscellaneous instructions. And there's a lot of patterns in this that you can exploit. This is a program which runs under CPM, but it's a full CPM. All it does is actually use the CPM effectively emit. The rest, what it really is a giant CPU test. So it sits in a loop, computing every instruction with huge numbers of different parameters and folding that into an enormous hash, a CRC. And then that is the result of that computation that the 8080 is executed. And that particular hash identifies the outcome in every single respect of the 8080. So for example, the 8080 has a bunch of flags. So every time an operation gets executed, that flag result gets folded back into that CRC, et cetera, millions of times. And then that gives you a sort of fingerprint of what it is that an 8080 does when it runs correctly. And this is interesting for the 8080 people because there's a lot of 8080 variants. Because you have to turn your mind back to the Cold War, the 8080 was reverse engineered by the Soviet Union. And I think it was an optical reverse engineer because it wasn't a very good match. In fact, some of the things to do with the flags they got wrong. And so the Russians have a bunch of 8080s that they want to emulate, but they don't exactly match the proper freedom-loving 8080. They're a bit different. So they actually get different CRCs. So this program actually checks that the 8080 instructions, so this each time it says, okay, it's done a CRC match and matched it for the official Intel 8080, not for one of those Russian versions, and then there's several other variants that produce different things, depending on, for example, how the carry flag gets handled after a logical operation. It's sort of a don't care condition for most programmers, but if you're going to do a high fidelity version of the CPU, you've got to match every flag. Speaking of high fidelity, there's not that much good 8080 stuff around. There is a lot of Z80 activity. Well, people have a strong attachment to the Z80, but the 8080 gets a lot less love because it kind of got eclipsed in the 70s by the Z80. They really, a bunch of engineers from Intel left, started Zilog, or Zilog, made the Z80, and then ate Intel's lunch as far as the 8080 went. So 8080 is kind of a poor cousin, so there's not a lot of 8080 activity. Eric Smith made one which passes that test, right? So that's the result from KSIM of it passing every single test of exactly matching. I should say that this test takes 3 hours to run on a real 8080. So this is actually a big investment for these people because, you know, their power supplies are dying. So they've got their ancient 8080 machine and they're running it for 3 hours in order to produce these official CRCs. So not to be taken lightly. So it runs it and it passes the tests. It's a full 8080 implementation and it's quite a lot of code. But it is accurate. It does do it all, including the crazy decimal stuff. Here's what it looks like. So here's an instruction, for example, which is complement the accumulator. Every instruction that gets executed in it gets told its own opcode so that it can customize its behavior. But in this case, it doesn't use it. So it has something there, the accumulator register, it exclusive ORs it with hex FF, and there you go, it's done its job, and then the next instruction can execute. And there is a 256 entry lookup table which tells it which opcode gets executed. So I think number 37 in that table is this particular function pointer. So it sits in a while loop, executing through this dispatch table, calling each of these functions. Here's something more ambitious. This is the old move instruction, that source destination thing. So it gets told its opcode, and of course it does want to do something different for each of the 64 different moves. It has to extract the destination field out of the opcode, the source field, do a special case if it's a memory fetch, it has to do a mem read, do a special case if it's a memory write, if the destination's memory, and it then finally does the assignment if it was a register destination. So 64 entries in that table point at this function. That's how KSIM does its stuff. That's all I have on KSIM, but I'll come back to it in a minute. And a historical digression, some people might have remembered this, because this made a big impression on people at the time, is, well, check it out. It's actually 2.5. So if you actually look at this stuff, it's all kind of quite bound up with the actual fourth implementation. It gets right in the guts there in order to create this assembler, and it doesn't bear close scrutiny. But this is from about 1980, and I think the OCR has lost some of the details, but it's mostly there. And what he does some preliminary housekeeping. Then he defines his registers up here, and then defines some instruction patterns, because there's only a few instruction patterns on the 8080, and that's what these words are here, these MI words, these builder words. And at that point, he's in business. He can define all of the opcodes of the 8080 on the next screen. And of course, this is pretty minimal. So each triplet here is the hex opcode, the instruction pattern, that MI word, and then the actual mnemonic. And that's how the assembler knows everything. So as far as economy goes, he's nailed it. And then that final screen is, he actually does a bunch of extra things. He does all the, he's got if, then, else, for example, there, right, in the assembler. So it's pretty thorough. So taking his model, you've got some sort of foundation. Then you've got the actual, I've got a slightly different task. I've got to emulate the 8080, and I cannot do it in 3 screens, I think. So I've got a lot more to do, but a similar sort of pattern. So what I really want to do is just say, for example, what is the opcode? I want to provide some code to do it, and then hook it into the table. So DX is an array, which is my 256 entry dispatch table. I've got something on the end here, which is semicolon op, which I use on the end of each of these words. And what that does is it takes the word I've just defined and then hooks it into the dispatch table at a particular point. So I say 2F, and then no name through op is the body of what I want to actually execute for instruction 2F. And op patches that code stores it into the array DX. So after this is run, then 2F in the table points at this piece of code. And I just keep on going, filling in that table with fragments of code to do the different jobs. So CMA reads the accumulator, flips its bits, and then writes it back into the accumulator. Going to the bottom, STC is an opcode, one of the random opcodes, which does sets the carry flag. So I store 1 in the carry flag, and that's it. STA is a little bit fancier. STA is store the accumulator into memory, where the memory location follows the instruction. So STA, it fetches reads the accumulator with RA@. It does a fetch 16, which fetches 2 more bytes, and then it's got an address on the stack. And then RAM store is the thing that writes into RAM. And so there's a lot of instructions like that which just have to be coded out, and it's fairly straightforward. Here is something fancier, though. Move instructions I actually use an opcode generator. So working backwards, so this do loop actually executes at compile time, and it runs through the opcodes from hex 40 to hex 80, which is the move group, and it invokes this generator with each of those opcodes, and it builds a little custom function to do the move. So I push I on the stack, I start my function definition, I call move, which is the move maker, and then I finally finish off the function. So it makes a little self-contained function to do that specific move. And what move does is it gets given an opcode, it pulls out the source and destination fields. R8 and W8 are the 8-bit, are the register read-write generators. And what you end up with is 64 small custom functions to do the register-to-register moves. That's all contained in these 3 lines of code. So contrasting that with KSIM, which has 1 C function to do it all, and quite a lot of fiddling around in the C function, this just has this generator which builds custom functions. So it's a bit quicker, and there's a bit less code involved at the source level. Okay, so going back to just a refresh on the ALU instructions, it's 3 bits of ALU field and then a source. So this is how ALU things are implemented. There's a function here. This is the generator, muck ALU, which pulls out the necessary bits to do the ALU operation, looks it up in this table of ALU ops, and then just does a compile comment. So there's actually this is the entirety of the ALU implementation if you don't include the low-level factors. So each line here is one of those ALU operations to do add with carry, subtract. So they all got factored out, and for example, the common code to deal with an arithmetic result and store it back into the accumulator is in a result. So all the arithmetic ALU operations end in a result, all the logical ones end up in L result. So this factoring led eventually, after a lot of hacking, led to the ALU operations all being one-liners. And that's the entirety of it. Okay, and that's how it gets generated. So that once again, it's iterating over that 64 instruction block, pulling out the source register. So this pulls out that source register 3-bit field. This compiles a register read, and then this calls the ALU generator function, and then we're done. We can finish the function. So that again generates 64 custom functions tailored for each register. So whereas KSIM tries to use a common function and avoid having custom functions for each one, in Forth, because we've got the compiler available to us, we can actually just generate these at compile time, these specialized function blocks. And so it ends up running, coming to about 225 lines of code. This is after I originally did a naive translation of KSIM, and it was about 700 lines of code. But of course, once you've got a test and some code which is actually passing that test, you can then just iterate and just keep on factoring. So coming down to about 200 lines of code, everything sort of became a one-liner. And sort of experimenting with something that Andreas pointed out, which is if you have one-liners, you can then align the stuff on the line to spot things which are factoring candidates. And that's what kind of happened with this. As it shrunk, it suddenly got a lot easier to work on. But the worst point of it was when it was huge. As it got smaller and smaller and more horizontal, it all became very much simpler to work on. There's not all good news, though, because as I was running KSIM, it takes 20 seconds to run that, what was originally a 3-hour test, which is that's a pretty good rate. But I'm running it on G4 fast, this is on the same machine. And I love Forth, but I don't love it that much. I don't love it so much I'm willing to live with 10x slowdown. And I was a bit disappointed with that. I think G4 fast on 64-bit machines is not that great, is my conclusion. It seemed to do very much better on 32-bit. I don't know what's going on. The other thing that occurred to me while I was working on this is that 256 lines is a great size for code because you can fit it on your screen. I'll take it. This, if you imagine, is my laptop screen. We all have screens of about this sort of aspect ratio. If instead of having a window with code in it, you arrange it as 16 screens, you can actually fit 16 screens on a regular work screen, on a laptop, or wherever you are. And then there's no more scrolling. There's no more moving up and down to have a look at your code. You can just have it all in front of you all the time, and just your cursor moves around on the screen. It couldn't be simpler. So that's kind of something I'm looking at now, which is taking Brad's block editor and taking out the scrolling, because who needs that? And making an editor which just lets you always edit 16K of code. That's what you got. You got 16K. If you go over 16K, it falls off the end. Don't do that. And it makes something, particularly on a PC, it makes, for example, undo quite easy. Because every time they press a key, you can just copy 16K into a side buffer. It's no big deal. So you could, for example, keep many keystrokes in a megabyte. So that's something I'm looking at now is a reduced editor. And I'm hoping I can get that editor itself fitting in 256 lines, which I think is an appropriate size for it. All right, so it was slow. I was pretty pleased with this thing, but it was not running especially quickly, particularly under G4. I ran it on VFX Forth, which is a proprietary optimizing Forth, and it ran much quicker. It ran in about 15 seconds, so slightly faster than the C version. So I knew that it's possible to get the thing running quickly and that it wasn't so much the code. There's something about G4 that is slowing it down. So I had a bit more time. So I started work on a port of swap Forth, which is the Forth that I have working on various microcontrollers running on a great big computer, the x86-64, which is where we're currently at with Intel. So this is where we're in part 2 now, something at the very beginning of Intel, and now we're at Intel's latest stuff. So things have changed a lot. It's like time travel. There's a lot of registers now instead of a handful. They also keep on adding in instruction set extensions, beginning with MMX in the 90s, and now they call it SSE. I don't really know why, because they don't do that much for you, but they do speed up some things, and they're super wide. So the one that's quite common now, SSE 3 or 2 or something, everybody's lost track, is 128-bit wide registers. So you can fetch 128 bits from memory and operate on them in one operation. So that's 16 bytes in a single instruction. You have to do the same thing to each element. You can't do 16 different things to your 16 bytes, but you can fetch them, store them, and compare them. More on that in a minute. And the other thing is that RAM isn't exactly infinite, but compared to the way things were, and maybe sometimes the way we think of as Forthers, RAM's really big now. And things like, I'll just make the dictionary small, or you don't bother. Because you could be writing Forth, you could take all the Forth there is in the world and fit it on a really low-end laptop. Memory is no longer a problem, so go nuts with memory. The other thing I found when working on it is that assembly language, which was once something in the 70s where everybody would write in assembler, and your principal way of working on the 8080 was to write assembler, is sort of gone. And a lot of assemblers for x86-64 are rubbish. They are assemblers for assembling the output of the C compiler, which is a very limited use case. So they're only good for the sorts of things that the C compiler does. So if you want to do something a little bit different, like use a tricky macro, don't bother, because the C compiler doesn't do it, and they're never going to fix your ticket. So you've got to choose carefully when choosing an x86-64 assembler. NASM, keeping the faith. You can actually write clever stuff in NASM. It all works. And they're actually on it. And NASM has a slightly difficult license, but I wasn't really concerned about that. I just wanted an assembler that I could actually use.
Also check out capacity as well.
Is that a free?
Yes,
Right.
it's also what they use to write the new FOS.
Okay, yeah.
But it's NASM is written in itself. So it's also a very fast assembly.
I do like things to be fast, but assembly time has never really. Yeah.
Should be, but it's not always true that the assembly instructions are one-to-one machine code, but fast and that is the design rule.
So common things, most of the swap Forth implementations are native code generators, so that's what I'm doing for x86-64. They all work the same way. I write a nucleus in host code which defines enough words to be able to start compiling things in high-level Forth. I need to get to a point where I can start to write colon definitions, and then everything else in is written in high-level fourth. So it's a sort of, it's a bit like Jones fourth. There's a bit of assembler which creates a tiny executable which can then run the compiler, and then everything else is just a big stream of fourth that gets fed into it. Trick for Linux and Mac is you're of course not allowed to write to code memory anymore. On the 8080 you could do whatever you like. Those were good times. But these days you have to switch off the memory protection, and this is how you make this incredibly arcane system call, and then you get a big block of memory which you can read and write and execute. So, although more on that, because that's actually turns out not such a great idea. This is the other thing, is that you can write position-independent code quite easily in x86-64, I found. And then all you can do is you allocate a giant block of permissive memory, take the kernel, which is about 10K of code, and then copy it into it, and then just jump to the beginning of the block. So no messing around with linking or relocation. Just once it's position independent, it makes life a lot easier. And then the fourth comes up, and it sees itself as the first 10K in a sort of megabyte of memory, and it's a very simple model for force allocation. All right, this is a good bit. So dictionary searching is a pain in forth, is a sort of effectively a string compare. But of course, on these machines, it's provided the dictionary entries are aligned, you can load the entire word, almost sort of 16 characters is quite a reasonable limit for a fourth word. You can load it into a register and then just walk through memory doing a single comparison for each dictionary entry. And this really is just one instruction. And it's definitely less than 1 nanosecond, even on a low-end x86-64 machine like my laptop. On the desktop, it seems quicker than that. So it is 1,000,000 times quicker than it was on an 8080. So if we look at an 8080 fourth, by the time it has executed its first few instructions of the dictionary search, it's just started getting going on the dictionary search, then the x86-64 has matched 1,000,000 dictionary entries. So it's quicker. It did okay, but it wasn't actually that fast. And one of the things which I don't have a slide for is I'd mixed dictionary entries and code quite intimately. And that's a really bad idea, because when you're writing into a piece of memory that's also a code piece of memory for the CPU, it really does not like it, because it's doing all kinds of amortization where it takes code and caches an optimized version on chip. So don't do that. So now then I take every dictionary entry and I put it in its own 64-byte line, and then the code afterwards. So it uses up space like crazy. When you look at something like the code for OnePlus, it's a 1-byte opcode and 128 bytes of wasted space. So it's a terrible idea if memory wasn't free, but it's a great idea for caching. So that suddenly got things running at a reasonable speed. It did okay, but it's not very fast, because my code, of course, I'm not doing any optimization at all. My code just looks like a lot of call instructions, one after the next. And doing that many calls kind of messes up the CPU. It's not that, it's built for running C code where the call density isn't that great. So obvious thing to do is to start inlining functions. So all I do is I have a bit on each word which says whether it's inlineable or not. And if it is inlineable, I just copy it into the code buffer at that point. It's not at all subtle. And there's another field in the dictionary which says how long the word is, how long the executable is. So all the inliner does is, instead of compiling a call to that function, it just copies in that function, copies in the actual literal bytes. But it's recursive, because if I finish compiling a word and I found all I've done is inline things, then that word itself can be inlined. So you end up with, if a word is made out of completely things that have been inlined themselves and doesn't have any other calls or anything else that stops inlining in it, then that itself can be inlined. So you can end up recursively inlining quite big things. To begin with, I put a limit on it, but as far as I can tell, it's always quicker to inline. There is no size limit unless you really, really go mad and you try to find some pathological case where you exhaust physical memory by making ever bigger inline functions. You might as well just inline absolutely everything. And when you look at people in the C world, which of course is what the chip is designed to execute, the dry stones benchmark, for example, has a bunch of function calls in it, but they're all tricking out their compiler. So it inlines absolutely everything, and you end up with this 50K function. And that's how you get it to run fast, is just not doing function calls. And it's the same in Forth. We like function calls because it implies factoring at the source level, but at the execution level, if you possibly can, just inline everything. That was a big speed up. So this is where I ended up with my competitive analysis. This is just running that same, what was 3 hours on the 8080. So swap Forth came in after I'd finished these optimizations, finishing it in 33 seconds, which is just about fast enough to use for an interactive test. It's a bit, if you're running a test and it takes 33 seconds, then it's very easy to look out of the window and lose your focus. I mean, it'd be much better if it was 0 seconds, but that's not going to happen anytime soon. So it was certainly a lot better than sort of go away and do some other task, which is what I had when I was working on it with G4. So what I want to do with the x86-64 optimizer is look more at optimizations. It seems it's actually quite close now to being usable. And one idea that occurs to me, because it seems a little bit less. So on the J1, for example, there's a lot of optimizers, a lot of optimizations that are quite involved. And it is fiddly. And it's very hard to know if your optimization has actually broken the compiler. All you can do is throw a lot of tests into it and hope. And it's the same. I work as a GCC maintainer now. It's the same on GCC. GCC has 200 optimization passes. And the way that they make sure that those optimization passes are good ones is just have an awful lot of tests. And if some of those tests don't exercise a particular optimization path, then it's just waiting to, break the brakes in your Toyota. There's just no guarantee that that optimization is correct. And we all rely on compilers in a fairly fundamental way. Much better to have a system which didn't suffer from that, oh, you weren't quite clever enough when you wrote the optimizer. So it's thinking about ways of taking the human ingenuity out of the optimization process. So what if you had a big catalog, and big, I mean millions and millions of entries, with a lot of Forth sequences of code and their equivalent optimized native code. Then every time you finish a basic block, you just look up if it's in the book, then you use the optimized native code. If not, then you fall back to the naive compiling version. And that is quite appealing if you could guarantee that every entry in the book is correct. So, for example, there's a piece of Forth code, and there's its x86 equivalent. Right, so it's using foo as a pointer, and then it's incrementing the destination of that pointer, which is quite fiddly in Forth, but there is an efficient x86 implementation of it, just because it's kind of an instruction set with a lot of possibilities. But actually taking that original code and then algorithmically deriving that second one is hard. And if you actually look at even state-of-the-art optimizers, they miss things. And you're just never going to get that 100% coverage that you'd actually expect to see. So what you'd really want is, if I could look up that sequence with appropriate templates for the variable parts of it, like foo, but the rest of it could just be looked up in a catalog, and it just picks up the native code to do the same job. And one way of doing that is to just generate all possible sequences of Forth, of which this top line would just be one of many, and all possible x86 sequences, and just prove their equivalence. Just find equivalence between those two lists. It's a big job, but look what you get at the. That's right. That's right. Then put it on. If that's your gigabyte, 100 gigabyte database, and it doesn't even need to be local. It could be on a server, and at that point, you've solved the optimization problem, and suddenly optimization becomes a very dumb process. It's just a table lookup. And there's people doing this right now. They're doing stochastic optimizations. They're generating random sequences which produce surprisingly efficient results. And they are using, I think they're using theorem proving to demonstrate that their input sequence and their output sequence are formally equivalent. That's where I ended up. Sure.
So,
Okay.
what are you going to do with all your efforts? What's your next step, if any?
Well, I think I'm going to probably try and get that editor going. And also the optimization thing is kind of interesting. So this is where all this led me to. But we'll see. But
Produce the code book for 8080.
that's I do, well, right. I do have an 8088 still running, so I could do that one. Yeah, that's all I have. Okay.
So you're actually maintaining a GCC?
No. I'm one of the roster of like many maintainers.
Oh,
I work on GCC.
Say,
Yeah,
wow,
there's a lot of us. a lot of people.
that's impressive.
No, it's not.
You know, trying to do a compiler, like a C compiler, it's like, ooh.
Oh yeah, but you'd think that if you looked at GCC, it's awful inside, and nobody understands GCC. I mean, there are literally parts of GCC that nobody understands. There's a file called reload2, which is not understood by anybody alive, and it's 20,000. It's got nobody. They're trying to work around it. There's a program to replace it with something written by people who are still.
Alive.
That's right.
It won't be alive by the time it's.
This is a problem. And
what is this done?
nobody knows.
If we turned it off, everybody would suffer.
That's right. It wouldn't work at all. It's to do with register allocation and register spilling. Is what the comment at the front says, and that's all we know.
It's a terrible mess on the floor with the register class.
That's right.
You know, it's interesting. The 8080, I took a class called microcomputers. The professor actually displayed on oscilloscope a clock cycle, and it takes 4 clock cycles to execute that thing. This is when it was running at 1 megahertz.
Yeah.
1 megahertz is nothing to sneeze at.
Well, let's just say, you know, because what he had done was, with class, we had to do signal processing. We had to do a digital low-pass filter. Digital. Okay. Which he said, okay, now for homework, you guys have to write your own 8x8, resulting in a 16-bit answer. And I just kind of went, oh, really? But because I had such an intense interest in it, I won the thing because I had the fastest multiplier.
8x8 multiplier.
8x8 multiplier, which resulted in a higher frequency cutoff. And it cut off at like
1 hertz.
2 hertz.
Okay.
I like that class so much, I could get next year where they had Z8.
Well, that's a dream machine by comparison.
Yes, running at 2 megahertz.
Right.
I did the full diagnostic software on cars in a expert system on a 2 megahertz AV. It was impressive. with foreign languages. It's all possible with mesh. Just bank in more memory.
You know, the 1980, I went back to Taiwan, and I brought the 80 form, trying to teach people how to import the 80. Don't get that. People say, what's 80? Nobody heard of it. What they learned from school, all the 80.
Really?
So nobody knows ADE. Because a professor in a technical school, he introduced a little board for the little professor. And he uses Z80 on the board.
Right.
Everybody in Taiwan will learn microprocessor in that board. So nobody knows about ADE.
Well,
God.
I mean, the thing is that it's kind of weird that Zilog, or did you guys say Zilog or Zilog? Zilog. Right. Zilog kind of cloned the 8080 and then gave it enough stuff to make it much more appealing, and then really cleaned up on the Z80, but then dropped the ball completely, and Intel took over again.
What they went was, they went to the Z8000.
Right.
Because I used that in my first job to do a display emulator.
Yeah.
You know, to take a direct view storage supermaker with Raspberry 3. And the only reason why they did that, the 68000 wasn't ready yet.
I think it's 80 got the next, the fourth next was machine instruction. That was the way out. So I think close, so it wasn't quite, yeah. But some people can employ some full time with that.
Not in the Z80, no, not.
6809.
No. It was the other, another different machine that has the fourth. Next, it's just said 6809. Now, 6809 came close as well. It had two stack pointers
Yes.
that you could use. But there was another, I can't remember it now, that had next and the jump through. It had that as two real instructions in a particular version of the ROM, the microcode, for a commercial processor. And it was out.
Yeah, that's right.
I don't think it wasn't Microsoft or Intel. I'm just blanking on it right now.
Like a 6502 that had 4 board
No, that was actually in the ROM early. No, this was in the instruction set. There was one commercially made chip that had Next as one of its microcode in the processor, and it didn't get enough use to make it viable for long term. Thank you.
Was that screen that you showed us before your talk?
The matrix numbers.
Numbers.
That's the actual machine, right?
Yeah. What is do this name for me. Just a random number.
Just a screensaver?
That was just right.
Random numbers, 0 through 3.
And random horizontal, random vertical. Right there you go.
Okay, next. Next is a break.
That's right.
All right.
Mr. Break.
We're on break.
Okay, so we're going to take a short break and we'll be back shortly. We're going to start really soon now.
Where's your microphone?
I have it.
He's ready. First, when you're going to start, Sam,
Yeah.
you need to tell us who you are. Welcome the folks back from the break.
Aw.
Be on camera or the screen on?
You can. I guess you can focus on me as I'm introducing and stuff. Yeah.
You stand in front of the screen to introduce yourself,
Well,
and then you won't have to move the camera.
that's just too easy.
Well, that never stopped us.
Yeah, I guess. All right. I'm on in 3, 2, 1.
God rival. I am listening, but you also hell up.
All right.
I
Well,
don't care whether you're listening or not.
all right. So I'm Sam Falvo, and I'm here to give a demonstration, not so much a talk, about test-driven development, what it means to do test-driven development. And the way I'm going to do this is I'm actually going to do live coding in front of everybody. And welcome back from the break. If you're just now tuning in, we had a break earlier, so there you go. Let me go ahead and start out. Well, actually, before I do any actual coding, as people may or may not already be aware, I'm working on a homemade computer called Kestrel, and one of the programs that already runs on the Kestrel is this little slide deck program that I call Milestone 2 for various historical reasons that I won't get into now. But I will say that one of the things, you can check this out up on GitHub. I'll include links on the mailing list, but it works by interpreting a display list. The display list is it's an ordered set of opcodes and operands. The opcodes are things like draw text here, draw horizontal line there, etc. And up until just now, the valid set of opcodes could pretty much just end and draw text here. There was no, I have opcodes kind of spec'd out for drawing horizontal lines, but I never actually implemented horizontal line before. So I'm going to attempt to implement the horizontal line primitive using some flavor of test-driven development and doing this live for probably the next hour or so. That being said, there's no guarantee that I will finish by the allotted time. And if I finish early, then we'll have another break, I guess. But that's unlikely to happen. So just to give you a description of my development environment, this is a Mac OS El Capitan environment. I am running my own custom RISC-V emulator that supports video and keyboard and stuff like that. You'll see me flip between windows frequently. Let's see here. Anything else that should come up? Oh yes, the build time unfortunately is not optimized. It takes about 3 minutes to build a ROM image for the emulator. So I apologize for that in advance. Before the talk, it used to take around 7 minutes. So I was able to get it to roughly double in speed by eliminating a lot of stuff that's irrelevant to this. All right, so let me go ahead and jump into what I already have. And let's see. There we go. Oh, come on. So we have a way of increasing font size, but not of decreasing font size. That's wonderful. Okay, so, well, I've tried that. It doesn't work. Oh, there we go. Yes. Okay, so I have this program called HL Tests. And basically, it runs under an operating system that I wrote called STS. Stands for Single Tasking System. You can, for all intents and purposes, you can kind of think of it as a simpler OS than CPM. It really doesn't do a whole heck of a lot, but one of the things that it does do is it verifies that your executables starts with a header, which is what I've highlighted there. And then it begins execution literally 8 bytes after that header. So one of the things that I do here is I store all of the important registers and pointers that the operating system gives us, so that if we need to exit early, we can simply, whoa, hello. We can simply restore them here and then jump right back to the operating system there. So that's a little bit of boilerplate. Now we actually get into the tests that I've written so far. So the first thing that I did to get this thing working was I wrote something that basically just did, okay, here's a string of text. Let me just dump it to the screen. That way there I know that this thing's actually working, or at least executing. And then in order to be able to draw lines, I of course need to translate from coordinates into memory addresses corresponding to the appropriate pixel in memory. So what I did was I defined one of these test cases. So let's ignore the rest of these for now. Basically what I'm doing here is something called inline parameter passing. So that is the assembly language subroutine call into the test procedure. And then immediately following that, I've got data. Now, this is generally frowned upon nowadays, but this is an extremely common programming technique for 6502 and 6800 series, because it basically allows you to code in assembly language, but at the same time, elevate your abstraction level up to something closer to, I don't know, say BASIC, somewhere in that vicinity. So if we look at the definition of this procedure, and it would help if I used the correct, no, I don't want that. I want HL. That's what I want. So if we look at the definition of this subroutine, we store our state, set up our critical registers, and it's a pretty basic implementation of the routine that you would expect to calculate the effective address containing a desired pixel. First thing we do is I multiply the y coordinate by 160. From there, I then calculate the floor of the x coordinate divided by 8 so that we can figure out the byte offset from that. We add those two lines there, calculates the base address of the video display, and then we add everything all together. Very, very, very simple. This is where things get interesting. And oh, by the way, so this is actually technically the code under test. Right now it's in line with the test procedure. I will be refactoring this a little bit later into its own procedure. So then we compare against our expected values, and if everything works, then we skip all the rest of this stuff. Otherwise, we'll go ahead and print out an error diagnostic, and we'll read out something called a grep tag, although STS doesn't really support grep. But basically the idea is if something were to fail, it would allow us to see what is going on. So if I do this right now, let me bring it up here. So this is kind of small for you guys to see probably. Unfortunately, there's, actually I could probably make this bigger. Let me try this. Okay, and of course it's not going to work for me now, right? Well, anyway, I'm just going to leave that as is. There should be a way to zoom in on this, and it's not working for me. So what I'm going to do now is I'm going to run this program. And we see here in this microscopic text here that it does actually print out, hey, this is H-line unit test runner. But you'll notice that there's no other output. So basically all tests are passing. That's how we know that all tests are passing. So if I were to change one of these tests so that it fails. So here, for example, I'm just going to arbitrarily choose a different and deliberately incorrect expected address. I'm going to rebuild the ROM image. Now, this is going to take about 3 minutes. So I can try to do a song and dance here if you want.
Why does it take so long?
The question was, why does it take so long? And the answer is because my assembler is written in Python and it's dealing with individual bytes. It makes no attempt to do block IO at all. So when I include binary images, so for example, the font that you see rendering to the screen, that is a 2K binary file, but it adds basically a minute to the build time of the complete ROM image. The other reason is there's no separate compilation. So when I build a ROM, it is literally one assembly file with a bunch of include statements, and all the includes are the component pieces. So every time I rebuild, it rebuilds everything from scratch. This obviously will be changing. This is probably one of the last years that I will be using STS version 1. And it will probably be the last time I ever use BSPL or my custom assembler. Recently, I got the GNU toolchain to actually work. So that will facilitate much more rapid turnaround times and allow me to use tools like Make and other build automation, such as Redo for that matter. I could actually use Redo for what it was actually intended for. So yeah, but once this is done and it builds the ROM-based file system, it will. I'll be able to execute this, and I'll be able to show you what a failed test actually looks like. Come on, you. I'm out of stuff to do.
How many lines of code is it? How big is the ROM, I guess?
The raw, well, the space allotted for ROM is about 1 megabyte, but right now I'm only using about 98 kilobytes of it. Yeah. So as you can imagine, it's assembling average, like if I give it actual assembly language to work with, it's much faster than if I just give it a binary file to include. But the aggregate speed is about 3,000 bytes per second, which is about as fast as a Commodore 1541 disk drive. And I really wish I could tell X Windows to open this on this screen. Awesome. What did I do? Nice. I think I just totally botched it. Okay. Let's try this again. Okay, so if I do /rom/ oops, PRG.HL test. So you'll notice that I have this extra line here that says ERR, and then there's this big old 64-bit hexadecimal value. So the idea here is if something were to go wrong, I can take that hexadecimal value, which in this case is 7 echo 570100, test 100 for those who are wondering. If I close that and then I come into prg.hl test.asm and I do a search, 7 echo 570100, boom, it just takes me right there, right? So that's the value of the grep tag. So this way here, if a test fails, I know exactly where to go in the code. So as you can see here, I've got some tests that are pre-defined, if you will. I've got tests for testing coordinates 0, 0, 1, 0, and 7, 0. All of these should map to the same byte address. And then as soon as we go to the 8th pixel, we know that we need the next, oh, I'm sorry, I didn't do my syntax off thing. We know that we should go to the next byte over, right? So which we can see here. Then, of course, I test the other corners of the display. Now, you'll notice I'm assuming a 640 by 200 display. In actuality, as you can tell by the minuscule size of the text, it's actually a 640 by 480 screen. But because Milestone 2 is designed to be a direct port from the Kestrel 2, which did only have a 640 by 200 screen, I actually spaced the lines out, which introduces the raster effects that you see. And then assuming everything works great, you know, we just return to our main program, which just follows through and returns back to the OS and everything is happy. And so that's kind of how things are going to go. So what I'm going to do now, so now I have, based on this, I've got some confidence that I can calculate based on coordinates where I'm going to be touching in memory. What I need to do now, which I'm going to start working on here, what is going on here? Come on. Okay, this keyboard is really, really bad. So now we've got our frame buffer calculations, some confidence in that. Now I'm going to be checking bit masking. So the idea here is in any byte, if the left edge of a line, well, let me do it this way instead of explaining it that way. So we have 2, 3, 4, 5, 6, 7, 8. Right? So we have yay ASCII diagrams. So we have here 0, 1, 2, 3, 4, 5, 6, 7, and 8. So the idea is when we specify a coordinate for a line, we're not addressing something like this, where we're not pinpointing the exact center of a pixel. Rather, what we're doing is we're specifying a range of things, which basically says I'm going to start on this edge and I'm going to proceed up to the 4th edge, if that makes sense. And that happens to include the interior 3 pixels. So for us, specifying a left coordinate, we look at the lower 3 bits. And calculate a mask accordingly. So what I'm going to do now is I'm just going to use the power of wishful thinking and pretend that I already have a test written for this. I'm going to call it start mask test. I am going to give this a grep tag of 0200 basically. I'm going to start with pixel 0 and I'm going to expect the mask to be set to 0 to FF. That is to say, if I start at this left edge, then I expect it to encompass all the pixels all the way to the right. So now if I were to, now in most test-driven development environments, the next step that I would do would be to save this file and then attempt to rebuild the image, knowing that HL start mask test does not exist. The reason we would do this is because if it successfully compiles, you have a problem. You need to choose a new name for your procedure, or you need to look at HL start mask test as it currently exists and see if it already does what you're looking to do, because if so, then that will save you a whole bunch of work. I happen to know that HL start mask test does not exist yet. So I'm going to define it. And right now, what I'm going to do, the first thing I'm going to do is do my standard subroutine linkage. And let's see here. Actually, that's false. So we have 1 word, 2 words, 3 words. 3 times 4 is 12. So I'm going to skip over 12 bytes, and then that will return there. This, by the way, is how RISC-V is able to accommodate inline parameters. For a processor like the 68000 or 6502, a lot of times what you'll see is that the start of the subroutine will pull the return address off into an index pointer somewhere in memory, and then they'll do whatever memory massaging they need to do, and then they'll add to that pointer, push it back onto the stack, or and do a return, or they'll just do an indirect jump. Either way will work. The nice thing about RISC-V is I don't have to do any of that. It's pretty much built in almost by accident into the architecture of the instruction set. All right, so I already know that if I were to do this, everything would look like a clean build because the test actually doesn't do anything. It'll just happily return and give the illusion that things will work. So what I want is I want to demonstrate actually how this thing works. So what I'm going to do, I'm going to grab the how am I going to do this here? Let's see here. It's offset 0, offset 4 from the stack pointer. I'm sorry, let's do that. 0, 4, good. And so what I'm going to do now is I'm going to take the low 3 bits, shift left. Actually, no, I don't need to do shift left. What I'm now going to do, though, is I'm going to calculate or get the address of a lookup table. And what should I call that? We'll call it left masks. Now this is going to clobber my return address, which I use here. So I'm going to hello. What is happening? Thank you. So I use S1 down here, so I'm going to continue to use S1 up here. Which means I'm now storing 16 bytes of state. Which means I'm going to need to load S1 with a copy of RA. And for consistency's sake, I'll change that to S1. Which means that this changes there. I guess it doesn't matter. We can keep that there. So let's see here, we take our low 3 bits. And I am going to add A0 to A1. So again, HL left mask doesn't exactly exist yet, but I will get there shortly. And I'm going to load an unsigned byte from that address. Then, assuming that I have that byte, my next step is to, let's see here, look at that. So that's 0, 1, 2 at offset 2. 2 times 4 is 8. So I'm going to do a load word off of 8 of S1. And if these two match, then start masks are A-OK. Otherwise, I need to go down. Otherwise, I need to copy pasta there. We're going to do an error. We'll make sure all of this is pretty much the same. And then to confirm that this actually fails, what I'm going to do is that. Actually, no, I'll keep the test case the same. And then to actually add let's see here. And now here, what I'm going to do is return back to our subroutine. But in order to do that, I need to load my address A1. Now here's the bytes. So if we start off with pixel 0, we expect everything to be set. And we progressively null out from there. So now, let's see how badly we damaged our file. So the idea here is we set up our masks left to right, basically, starting with all ones, because if we start off with a pixel on an 8-pixel boundary, we expect all ones heading in a rightmost direction. And that's what that little table does. And if we execute this, theoretically, everything should work. Normally, you would want to develop the test so that something would fail. That was, in fact, my original intent. But I'm so used to doing this. I'm just going to let this go so that we don't end up blowing another 3 minutes. I'm going to queue this up.
So you,
Mhm.
can you in plain English say you want to draw a horizontal line?
Yes, that's the intent of all this code is for.
Okay, so you're going to see a bunch of a horizontal line on the screen, right?
Well, that's hopefully.
Okay, so what's the test that you wrote?
So the frame buffer is allocated as a series of bytes.
Yeah.
The CPU cannot just set a bit. You have to read in a byte. You have to logically OR in some kind of mask, and then you store that byte back.
Okay.
Otherwise, you'll affect pixels that you may not be interested in changing. So the goal here is to calculate for a given span of a given line segment, the left edge and the right edge separately, and then fill in the gap between them with all ones. The middle part is the easy part. That's just looping through memory and setting everything to FF. The left edge and the right edge involves the read modify write algorithm. What I'm doing here is I'm attempting to make sure that my mask, that the settings that I use for my masks are correct,
Okay.
if that makes sense. However, with my luck, this will probably crash. And it does indeed work. So that's good. There's no error messages. So now that I have a working prototype here, it is now a simple matter to just, let's see here, 7F, to just replicate this code. This is fairly, you can't really get around copy pasta here, unfortunately. Now, because I am doing this so thoroughly, this actually will exhaustively test this particular functionality. So instead of replicating and testing, I'm just going to move forward with the right hand mask after this. And the other thing that I forgot to do was adjust these so that if any of these did fail, we would have correct stamps on them. Okay. So that was the start mask test. So let's do the end mask test. We'll make that 3. And then because that's not terribly interesting, well, yeah, actually, yeah, I'll just leave that as is. So basically, again, if we consult our little diagram up here, if our pixel position starts out on an even boundary of 8, because it's right on this edge here, we don't expect any pixels to be lit up. So when I actually invoke the end mask test, I do in fact expect 0 to be the result. Interestingly, I also expect the same thing to happen if I give it a pixel value. Now, there is actually a way of calculating the end mask based on the start mask. So I'm going to, oops, where am I here? Oh, and now actually, let me refactor this. So let's hear start mask okay if we're here. Otherwise, I can say branch if not equal, test fail. And then all of this oh my God, stop it. Okay. Da-da-da. Let's see here. Where are we here? Okay, here we go. So I will. So now we've eliminated some duplicate code there, which is good. Which now allows me to more easily so now we have that. Da-da-da. And just for sake of argument, I am going to leave this as is. And this will rebuild. And I expect this one to fail. This one I definitely expect to fail. So what I am going to do here, let me see, check my notes here. Okay, so that's what I thought. What did I think? You'll find out as soon as this test fails. So basically what we're going to see is that on the right-hand side, when we're calculating the end line segment, it's essentially the exact same set of masks that we use on the left-hand side, except we invert all of the bits. And that should give us what we want. This should be almost finished. Three minutes turns into an eternity when you're giving a public demonstration. Oh, the flame screensaver is coming next. Okay. Oops. And sure enough, it fails, and we have the expected grep tag. So now, so I'm going to do this. So since I know that this is going to work afterwards, and we're going to expect that to be 80 because we're filling in from the other side. That goes to C. This has 8, 9, 10, 11. Okay. And so just for sake of ease, I'm going to replicate everything there. That becomes 12, 13, 14, and 15. Okay. So now our end masks is calculated exactly the same way as we did before, except we flip the bits. Oh, check this out. And in fact, we actually don't even need that label anymore because nothing references it. So now we've got 8 more tests defined. These should all work. We'll find out in another 3 minutes. No, this is time spent assembling. This is I/O time is instantaneous because it's reading from ROM file system. So like it's not even touching I/O. It's only 98K, but is ridiculously slow for byte level I/O. Yeah.
What we're supposed to conclude from all of this. And
well, basically,
help our lives. And
well,
message, big picture is.
Well, the big picture is this is what test-driven development software development looks like. You start off with a test, you make sure it fails, you make just the minimal amount of code changes needed to make that test pass. You rerun the test to make sure that it passes, and you rinse, you rinse repeat as necessary until you finally have whatever deliverable you want. And right now, so I've gotten enough testing implemented that I know that I can trust the left edge and the right edge. Again, filling in the interior portion of the line is simple enough. I obviously won't be able to demonstrate the actual drawing of the line, but I know that my bit masks are correct. So actually implementing a line draw should be very, very simple. Just, refactoring the code, making it into, more procedural, a more modular design is very easily done with this.
How do you know that the test corresponds to the actual requirement?
I define the requirement. So so basically the idea is, let's say you were the person who defined the requirement. I would have to sit down with you and actually go over and say, these are the tests. Okay, we're working on this. There's a common expression that we ask in the industry, and that is, how do we know we're done? And if you can answer that question, you can usually codify it in software somehow. So for example, in the case of line drawing, if we draw from pixel 3 to 8, then we know that pixel 0, 1, and 2 must not be modified. So that gives us 8 test cases right there that we can exhaustively test this with. You see a prompt, and now there's another prompt. And everything works. Excellent. So I'm gonna wrap it up here. So even though we didn't get to the point where we could actually draw a line on the screen, we have all of our components, the individual pieces that make up the line draw procedure test, and we have full coverage. Now, in a more sophisticated development environment, you would rely on analysis tools to be able to say, okay, we've got this body of tests. What are our holes? And you would write test automation to fill in the gaps, basically. Greenfield applications, things that are brand new, like I mentioned, I would sit with you, go over your requirements, and actually say, okay, if I were to write this, how would I know you were done? Or how would I know that I'm done? And you would typically say, okay, well, let's say we draw a line from pixel 3 to pixel 8, and then we would negotiate test cases based on that. Once all those test cases are done, that's how we define done. And that's test-driven development, live in action.
Thank you, Sam, for letting me torture you yet again.
Well, and thank you for bearing with me in the 3-minute builds and torturing everybody who's watching this. I'm sure they were probably sleeping and falling asleep at the keyboard.
But your tests pass.
That's true. All of my tests pass.
But you still don't have what your goal was. So how do we know that we're done? And the answer is we're not.
We're not done. So there are still more tests to write. One of those tests is if I define a buffer in some arbitrary memory location, and I draw the line from pixel 3 to pixel 8 in that buffer, then I expect the buffer to look like this this image, basically.
Have you had any experience with these programming languages that allow you to write a requirements document in this special requirements document definition language, and then a compiler comes and takes the requirements and produces code from them?
Yes, there are several like that for the Ruby language called RSpec and Cucumber, depending on what level of abstraction that you want to go for. There are similar tools for other languages as well.
I get the sense, though, that you write some requirements in one of these languages, and it's hard to imagine that you're really asking for what you think you're asking for.
You have to code review for sure. I mean, none of these tools, I mean, like they don't automatically write the tests for you, but they will largely eliminate a lot of the boilerplate necessary. So at some level, you still have to write actual executable chunks of code. So like, for example, in Cucumber, I could say something like, given X, I want Y so that Z, or something that's vaguely English-like, but still machine parsable using regular expressions. And what it will do is it'll take I want Y, look it up in this dictionary, if you will, and it will actually use the code corresponding to that, suitably parameterized for that test case, and it will execute that code. So even though you don't actually write all the possible test cases, you write all the individual pieces of it, and then whoever's responsible for the test cases is responsible for building everything else.
How do you do this with top down? When you top down, you say, I want to see a straight line, you don't see it. Now what? So your testing basically has to be from bottom up, right? So
in my case, I'm testing from bottom up because this is dealing with bits and bytes, and it makes more sense to do that. But if you wanted to go top down, if you follow Niklaus Wirth's approach, for example, what you would do is you would actually write the top level test case first. I have a frame buffer in memory. Here's my frame buffer. I draw from pixel X to pixel Y. I expect this frame buffer to look like this. And so you would basically recurse down and down. Now, in this case, the minimal amount of code necessary to make that test pass would literally be just copy a block of bytes into that. And then as you refine as you apply stepwise refinement, you would actually write more test cases, make sure they fail, because they will. I mean, if you're just doing basic dumb block memory copy, and then you would actually sit and you would actually go and write or possibly rewrite the implementation to satisfy all your tests. So it is doable. I've actually done both ways. In this case, I'm doing bottom up just because it makes more sense for this purpose, based on how I think. But for other people, it might not be. Anyway, I don't want to take up too much of your time. I have exactly like 30 seconds left on the clock. So without further ado, I'm going to pass the baton to Brad Nelson.
So, hello everyone, I'm Brad Nelson. So, with a new year upon us and time ticking by, I thought, need to get organized. That's, a common thought at the beginning of a new year. And so, that's that same thought occurred to me. Slide this over a sec. Managed to forget my clicker. The trouble is, of course, how to do that. And in the past, for those of you who know me, I'm kind of the sort of person who tries to keep things in my head. I'm actually very bad at writing things down. I'm very bad at organizing the world external from me. I have a tendency to think I can keep it all in my head, and I'm at an age where I'm well aware that actually doesn't work. And so it's something about myself that I'm endeavoring to shift ever so gradually. So there's all sorts of systems of organization in the world, and a calendar is one that does surprisingly well for a number of people. I mean, I think I think back to the first sort of real job I once had, and I actually was actively bad about not even using the company calendar and such. But my current job, I managed to sort of get by on a calendar, although as I often tell people, my calendar is a pack of lies. So it's very often there's this mismatch between what I mean to actually plan for and what's there. I mean, people can schedule meetings with me and such, but they have to sort of read between the lines about what I'm actually planning and thinking about, and when I'm actually busy, and what I'm actually focused on. There's people who manage to keep a diary, and I've always admired that. But if I could get there in baby steps, maybe. But it requires a little too much ability to sort of step back and find that moment where you really remember everything that happened today. I tend to be thinking about what just happened. So maybe it's a question of frequency. If you're keeping track of things meticulously, maybe a ledger, keep notes, clock my hours. I've never worked as a contract employee. I can't imagine clocking one's hours might actually, in some ways, make things better. And then there's the sort of big ones. You can keep an encyclopedia of all the things. And I did a little bit of sort of thinking before I stepped into this about what would be realistic for me to try to do, and what's out there. And I came across this idea that used to be very fashionable, apparently 300 years ago, called a commonplace book. And the notion is it's a little bit like a diary, and I'll talk about it more in a moment. But it's subtly different. There's other things. There's a notion of a tickler file, right? You keep your sections for this, and this is the sort of mechanical equivalent of the calendars. And people used to be fond of this. And there's something to be said for actually viscerally having a card. And there are times when, particularly with projects that involve other people, I sometimes almost wish for the physical artifact to manipulate. But I'm unlikely to stick with it if it's an artifact that I can't carry with me, and so that almost necessarily means the phone in my pocket. I toyed with the notion of a Franklin planner, right? One of these sorts of things. Oh, I'll keep a daily, task list and all of this, and I actually one I didn't even put it in the slides here. Kind of a similar. There's this tool called org mode in Emacs, and so in my brief stint of okay, let me give Emacs another try. Let me give org mode another try, and then got all my stuff and my to-dos organized in it, and then fell off the horse. And it's very flexible. It had some desirable features, but the one that kind of caught my eye was, for some reason, at least in this year, was a commonplace book. And the idea with it is it's a place to store fragments of text, often borrowed. And so it's sort of like a diary, but it's a diary where the idea is that you're sort of organizing it by topic, and you potentially have the notion is to have an indexing scheme so that you can find things. And this is a computer technique for doing so. And there were a number of indexing schemes, but one that really caught hold of people's imaginations was one that John Locke came up with. Where you would organize things by letter. In fact, this is actually one of the precursors of people even having things like
indexes in books and things of this nature. It was, you know, considered somewhat innovative and radical to actually have an index. And the way Locke's scheme worked is that you would assign every entry a heading, and you would then keep an index that you could keep in 100 entries, where you would record a mapping from the subject heading, for a given subject heading, you would essentially hash it by taking the first letter and the first vowel, and then you would record which pages, sequence of pages, contained entries with that hash. And so you could, for each of the consonants, and he would actually, the reason you get 100 is he would pack together some of the consonants into buckets that, you know, made sense, particularly in a world where U and V and I and J, you know, are mostly the same thing. And there was he was very efficient. There's an empty slot around very few words or start with ZU, and so you can use that for QU. And so you would organize things like this. And the idea is that if you, the index could really fit on 2 pages, because you would typically mark the start of a page containing a certain hash, and then you would, there would be an annotation to say, turn to the next page for as many pages as you filled with that. And then if you ran up against another entry, you would have to add another entry in the table of contents for this. So obviously I don't want something nearly so broken in the computer, but I feel like what was interesting about this kind of a system is that it's kind of like a diary. You're making an entry, but you're entering things when they catch your interest, when they're sort of at a level of granularity of almost like a tweet. And so, and in fact, people would use these things. There was about a 200-year span where this was a relatively popular thing to do. In fact, they would, you know, even have little courses in universities and whatnot to encourage people to do this in certain ways. And the idea was this would let you collect, you know, interesting quotations or interesting factoids that you had encountered. Apparently, Ronald Reagan used to have a similar notion that he would do it on note cards, and he had a big file of a big case full of note cards with individual quotations. But oh yeah, and so the mapping looks something like this. So the one sort of special rule is that if a word starts with a vowel, then its primary vowel is also the initial vowel. And then you know, for something like stars, you skip over the T to go to the first vowel. So you'd organize them into buckets like that. So, but of course, you know, I want something that can actually help me figure out what to do. So I do have this sort of general aspiration that, well, I want to keep sort of entries on things that keep me interesting, that I find interesting. I might want to generate a task list. And I've really had trouble in the past with simple to-dos, strangely. Says something about myself that I'm even the guy that can't even manage to consistently keep my list of to-dos in a document somewhere on a page, and I'm terrible with issue trackers too. There's, you know, different people have notions of, you know, maybe you prioritize them in different ways. Because one of the problems is I just put everything, whenever I do a to-do list, I pour everything into the to-do list, and I don't sort them. I don't have any sense of, you know, what's important, what's not, or which things are, you know, which things are urgent. You know, you could get really fancy. You could do a Gantt chart. You know, you keep your pride, organize your life. Yeah, everybody's gonna get a good laugh, right? Just, but you know, some yes. Mm-hmm. Mm-hmm. I kind of tried this, like when I was, for instance, when I was doing org mode, it had a flavor. That was kind of the flavor of how I tried to use it. But I think one of the issues is that I'm very flighty in terms of my willingness to go back to a particular place I'm okay with entering things. I'm dreadful at going back and consulting them later. So I should say, by the way, that notion though of the rolling it forward is actually with a tickler file was one of the notions that you would potentially have your load of things to do today, and then you would, you know, put them you'd have a set of cards literally, and then you might bump the ones to tomorrow that you couldn't do today, or you bump them a week from now if it was something, you know, this sort of notion. So I definitely have toyed with some of those kinds of things, and I'm, as you may have noticed here, my goals are a little wishy-washy, right? Am I trying to organize, you know, what I'm going to do? Am I trying to remember things I find interesting? And I think, sort of broadly, what I think at the core of it, what I'm really trying to do is get more of my thinking in an external place as I find that I'm no longer able to keep it all up in my head. So, but anyways, yes, a Gantt chart, you know, obviously. Indeed. So Gantt chart probably over the top, but I do kind of wonder, you know, something in general that I have speculated, particularly about myself, where I'm really unwilling to go and consult with references, is the more that the collection of the information can be automatic, and that I can sort of glean something after the fact. It may also be useful. I've often wondered if I, you know, kept an automated log of what directories on my system am I currently sitting in? How much time do I spend there? What was I doing on that day? You know, because I've definitely found myself trying to go back through my emails and say, what was I doing this week? I don't, you know, doesn't make any sense. One remarkable experience I had is I had this watch that I stopped using, you know, shortly afterwards because I found wearing a watch was not useful. But one of the things that it did early days is I got a new phone, and then I got the new watch, and I had to sort of reset everything back to factory settings because the two wouldn't talk together. And one of the first things it did is it said, "Oh, you need to walk, you know, this many more minutes today." And I found that with the machine actually telling me to do it, I had kept with it. And so maybe if the machine tells me what to do, that would help. But in any event, at some point I said, okay, well, I got to start writing some sort of piece of software, because this will, of course, you know, either fall out of my head and I'll stop thinking about this and think about something else. So I started writing software, and I had this on App Engine, the space of names are slightly less gobbled up, and so this nominally valid English word, you know, something that's iambic in character, was not taken, and so I grabbed this and used it, and I'd actually been sitting on it for a while. So that's where I've stashed away my tool for the moment. Well, so what did I try to do? I tried to make entering notes something that could be done very quickly, and I wanted it to be something I could do everywhere, because I have this other nasty tendency that I will, you know, some people have so I know a person who speculates that every person has sort of a primary computer, that's really where their own external state is. And I'm actually kind of weird. I don't know that I have that. I have a tendency to, I'll leave a couple files here and a couple files there, and I forget where I've put things. And so I need something that will help with centralization. The other thing is that many years ago, I took an art class with doing pastels, and I really enjoyed that. And it's something where the amount of bother and to do of actually having the materials present was a hassle. And so I've always been frustrated with the drawing programs that I have around. And so I wanted something where I could maybe try to do a quick sketch in a way that resembles pastels. And of course, then maybe I can use Forth to help me aggregate this together. And if I can sort of make things more coherent out of the incoherent mess of what's going on in my head, then things will get better. So so what I actually created is a web app, and it has sort of the option to install to the home screen. And I've also used this as an opportunity to, you know, further refresh my knowledge of the latest in there's a notion of web app manifests, where now you can install a web app to your home screen on various phones and whatnot, and they'll have certain properties in terms of how they appear and how much like a native app they appear. So I've been sort of learning about that. And the big thing is I wanted to make sure I could cache local state for offline use, because I'm also sort of bad about being in places where my connectivity is dicey, and I want to be able to have it work everywhere. But I want to sync it to a shared place, because I need that one place to put things, or else I'm going to get confused. So there's a client, and then there's the client is, you know, JavaScript, and then sort of a fourth on top of that, and fourth in the very broad, vague. We'll get into that in a minute. And then a server that this time, just for fun, I did it in Go, just because they support Go, and I hadn't ever done any App Engine stuff with Go. I'm using App Engines just because they're, well, for small applications, it's free, and it's, why not? It's one less thing I have to forget to not forget putting a coin into. So the storage the way I've decided to organize things is I'm storing things in the App Engine data store, and it has interesting properties. You have a collection of entities. It's a sort of one of these NoSQL type data stores, and you can look things up by a key, and you can look them up by indexes, and you can keep indexes on various fields. And so the kind of entry I'm keeping is, well, a timestamp of when did I think this thing and record this thing, and then a blob of bytes, because really that's all there is. But inside of that blob of bytes, I've unfortunately acquired a little more structure. I've ended up sticking a modified timestamp and then an optional image and then some plain text within that. And I'm probably should have had more structure from the get-go. One of the reasons I kind of did it that way was I had this vague notion that I might want to encrypt what's on the server, but not worth the trouble. Anyhow, so then on the client, I'm using IndexedDB. I hadn't ever done much before with IndexedDB. And I mainly did that because there were sort of succinct ways to ask for more quota on all the various devices on the phone. I could say, let me use 100 megabytes of storage for stuff. And it's actually very sort of similar in a way to App Engine storage model. You have entities, and you can look them up by key, and you can keep indices on them for various fields so that you can kind of walk through them in some order. And on the client, things are a little bit more splayed out. I mean, I'm keeping the timestamp and the modified timestamp and the image, and the plain text, but I'm also recording what key has the server stored this under so that I can match up entries between the server and the client. And the key thing to remember is that I want to be able to I want to be severed from the server, be able to record an entry, and then later be online and have the client store that to the server. And similarly, in the meantime, maybe I picked up some other device and made some entries, and I want them to all eventually catch up to each other, and so be eventually consistent. And then there's a local key. So I'm needing to, the server key might not be there if I haven't yet deposited something. Oh, and there's one more field, critical thing, a pending flag. And the pending flag means this is something that hasn't yet been synced to the server. And so you'll notice if you're thinking through this here, there's a little bit of a problem here if you allow modification. And I toyed back and forth with, do I want to allow modification? And after a little soul searching, I decided that I did in fact want to allow modification, because in the past I've dabbled with sort of similar thoughts, and every time I think it through, it's like, what would I do if I had some entry and I kind of want to make some modification to it? And, so anyways, if I allow modification, anything that's local that's pending means that it needs to get out to the server whenever there's a connection. And then you may have a server key for it if it's some existing entry that the server knew about or not. If you do have the server, well, so let's talk about how sync works. So, so you sync writes by, you upload all the pending items. So that's easy. You can go to the index for pending items and find all the ones that are pending. And then you can, if you send up an item, if you have a server key for it, you send it along so that the server knows to cover the old entry. You can have races. If I modify an entry in one place and not in the other, and I haven't synced in between, that's probably not good. I'm a little bothered by that, but at the end of the day, can't worry too much. Because the alternative is I have to have some way to resolve conflicts, and that would be hard and complicated. And then if it's something new, then the server is going to generate a key for it and tell the client. And so at that point, I need to remember that key going forward. And then at that point, I can unmark the item as no longer pending. For reads, so I just find the newest local item. I can go to one of the indices for commit date, and then I can just ask the server, give me all the items that are newer than this date, so I can pull them down and keep them locally, and then assign them a local key. And that process can go on in the background and keep things happy. So
Can you go back to the thing about, so you have conflicts, right?
yes.
Okay, you went too fast for me.
Ah, yes.
So we upload stuff, get an included server key. oops, somebody else has used that server key. There was a
So the intention is that if you're modifying an entry, you could in fact have the same server key. And so the issue is imagine you have two clients, and say I've edited an entry on both clients, and then they both go around to push, and I made the edit based on the original state, but now I've got two separate edits. They're going to collide. Somebody's going to win, and it's just whoever syncs last. This would definitely be a problem if this was like a collaborative document that I was interacting with somebody else on. But my primary thought here was that, well, this is mainly for my own personal use. This is something where if I did modify an entry in one place and then later modified it somewhere else and there's a clash, that would be bad. But hopefully that will be an incentive to me to keep the entries small and separate. And so that's, yes.
But actually, you wouldn't really have that problem because if you store the timestamp, you can actually, whoever has the timestamp.
It's true. I could actually resolve a winner.
Or you could store both of them as like a histogram kind of thing where you can actually roll back your changes.
I did, in fact, toy with the idea of keeping around both copies in the case of a clash. Right. Yeah, no, and I have toyed with that. So how to deal with conflicts is actually something where I worried a lot about it before I sat down to write the code, and now the different options. That one is probably the right one. The keep them timestamp, and probably just keep both if there's a clash, right? If you actually hit. Right. And of course, that'll require keeping one extra field, which is you need to know the date of the guy that you like. What was I modifying? Was there a clash? And there's a little bit of an extra wrinkle in there because imagine you've got an entry that has not yet been up on the server. Are you going to? There you can assume it's all local, but anyway. So yeah, there's lots of ways to sort this, and I worried about it a lot before I implemented the app, and I've had a couple of glitches, in fact, bugs I've actually had. But if anything, I've tried to write the code in a very conservative way so I don't lose stuff, right? That was. So it's actually just a sequential stream, and so the idea is that I'm going to impose order on it separately.
So if it's a stream and you maintain the stream, meaning theoretically you can do an undo, then
yeah. So yeah, and the one of the other conundrums I had is that I was particularly as I'm thinking about storing images. I knew that I wasn't going to be able to do any automatic, merges or anything like that. But I was also a little bit worried about storage space. And in fact, that's actually kind of it's funny, here talking about unlimited storage, but it's amazing the difference between text and images and how rapidly with images you can burn through sort of numbers. And so that's something I'll mention in a bit. Yes, pictures are fun. So as I mentioned before, drawing, see, this is a perfect example of my inability to focus on one thing, this sort of hummingbird kind of thing. And so while I was in the midst of this, I pulled in another problem that I've sort of long thought about looking into and never got around to, which is, so pastels, for those unfamiliar, it's basically pigment and a little binding agent, and you put it on paper. And the nice property about it, especially for artwork, is that you can sort of rub it around with your finger and it sort of blends, or you can use a small eraser and rub it around, and it potentially does. If you press lightly, it doesn't erase it. It actually blends, and if you push hard, you can sometimes scrape it off. And it has all kinds of lovely properties in terms of drawing. And it's a similar sort of the colorized version of it, similar to charcoal, has some of the same properties. But pastels are kind of the color version of this. And so I wanted to mimic that, and I've often, I've seen a number of drawing programs that attempt to duplicate natural materials, and they sometimes do charcoal. And I've yet to, and I confess I haven't done an extensive survey. I'm sure someone out there has probably done pastels really, really well, because I know this is an area where people put energy. But at least in my sort of cursory awareness, I hadn't encountered any that I was particularly pleased with. And in some ways, I'm not really looking for the real thing. I'm looking for sort of my own mental, sort of idealization of it. But basically, yeah, I wanted that blending, smearing, and mixing. And I've got the phone in my pocket. I got the touch screen. I want to be able to just do that. And the other thing is it's touch screen, and I don't really. I'm not trying to do a whole image editing program on the device. I want something where I've got a couple of brushes, and it's in some sense I want fewer brushes. I want minimalism of just something for the quick sketch, something for just to play with color. But I ran into something, and I kind of was aware that this was an issue, but I kind of decided to confront this. And you'll notice this is a complete, 180-degree turn something. I don't know, why this is in this talk. So, color mixing is tricky. And, RGB, if you mix it, it has, if you're treating color as RGB, that's an accurate depiction of, in one sense, but it's an oversimplification. It's an oversimplification in the sense that our eyes are responding to these primaries, but there's a lot going on when you're talking about actual real materials. And the other issue is that there's a distinction between how RGB is accurate in terms of light mixing and hitting your eye. It is not accurate in terms of substances mixing and their interaction. And the other issue is just as a color space, it potentially is the wrong place to be doing the kind of mixing. You can kind of get something nice in terms of the sort of mixing properties of materials if you're doing things in hue, saturation, value space. But it actually has some weird quirks in terms of mixing as well, because then you kind of get this thing where you're kind of curving around the rainbow in strange ways. And the reality is that there's actually an extensive body of research around this whole area that goes way back, and there's a very precise model for the mixing of pigments and their reflectivity and how layers impact each other in huge amounts of detail. There's some kind of 6-parameter model that these fellows came up with a long time back. But the tricky thing is you want something interactive. And there's a company that I guess has a product called Paper, and they actually have an interesting blog on their efforts to explore this actually approximately the same problem. They were mainly focused just on a color picker. They weren't even necessarily interested in mixing directly on the surface of the page. And they explored a bunch of different options in this space. And they tried implementing this. And the thing that was frustrating was that it was, aside from being incredibly slow, even that sort of failed to, the tricky thing about real materials is you hold them in your hand, you kind of have this expectation of, okay, this pastel kind of, this one kind of overcolors this other one in various ways. And so what they discovered was that for their product, at least, this idealized model, at least with the parameters that they were easily able to feed into it, wasn't very satisfying. And so what they ended up doing for their product, this is a kind of an interesting turn in the same direction, is that they said, well, let's just do this with measurement and data. And so they actually ended up producing tons of paint swatches, mixing, and then digitizing these and creating a big database, a big lookup table. And so, because they found that this was, they could find a particular material that they found personally satisfying with how it mixed, and that was an easier way to capture the properties than trying to come up with some model and find the right parameters to tune it. Well, I didn't want to do this because that sounds like a lot of work. So I kind of dabbled around. And so let me actually, I kind of glossed over what the problem is, and you may be thinking what's the problem here. So additive color, is the sort of usual thing you think about with on computers and displays, but actual substances on paper do something a little bit more like subtractive color. But even subtractive color is kind of an idealization. I mean, when people do printing, they go to incredibly great lengths to get materials to produce very particular pigments to get very precise cyan, magenta, and yellow pigments for subtractive printing. And even when they do that, they don't get perfect black, and so they typically will add black ink to get a more precise black. But on another level, fundamentally, what they're really doing is they're trying to avoid the problem of how actual inks and pigments mix by having very pure substances that don't mix, that just layer, and so that the RGB model, in some sense, conveys itself to paper as closely as possible. But the reality is that the sort of artist's instinct of the primary colors of being red, yellow, blue it bears a greater relation to reality than you would think when you actually sit down with real substances, because very often the tones are not pure. They have different responses at different frequencies. And to paint a sort of, to paint, actually skip ahead a slide. The underlying issue is that when you're mixing together pigments, a lot of things are going on. You've got different flecks of pigment of different color. You've got light coming in, and maybe the light hits a particle of pigment and bounces back, and so then it's effectively just additive of what percentage of those. But sometimes it goes in, and they're semi-translucent, and it bounces around, and so there's really an additive component and a subtractive component, and this is happening at all the frequencies of the spectrum, and your eye is responding at different levels to each of these. And and on top of that, there's like binding agents in here that are sometimes translucent and sometimes opaque in various degrees. So there's a lot of complicated things going on. But on a more basic level, the real sort of psychologically frustrating thing is that when you do sort of simple things for mixing is this, and this is actually the least objectionable, right? If you take magenta and green, in RGB space and in CMYK space, they meet in the middle and they're gray. And that's a little counterintuitive, but what's even, and this similar story here, this is actually the closest one to being sort of matching your intuition. And in fact, artists will use complementary colors, although even there with real pigments, you tend to actually have a little bit more of an orange color with real substances in terms of how the mixing falls out. But where it really gets bad is blue and yellow making green. That's and if you've ever mixed blue and yellow paint, you're aware that it actually kind of does make green. Now, it doesn't actually make sort of ideal perfect green always. It depends a lot on the pigments. And in some cases, you actually get a green that has a very gray sort of shade to it, because it's there's that combination of additive of the things reflecting back immediately and subtractive. And there's a lot of actual active research. I mean, there's papers fairly recently about trying to model that precisely. But the underlying problem is that you have the psychological expectation, if you have had experience with physical substances, that blue and yellow is going to make green. So, and there seems to even be different emphasis on how much of the problem is this question of the layering, and how much is just that you've got the spectrum of blue substances have a range of colors in them, and yellow substances have a range of colors, and some of them fall into the green range, and so if they're blocking some of those, you're getting green there, but you're also getting other effects mixed in.
When you mix it in the drawing,
Mm-hmm.
you got that triangle there?
Yes. So these are meant to be response curves. So actual substances don't emit a single frequency of light; they emit a range of frequencies, and your eye also has another curve that it's integrating for how it responds. And so the different layers have the potential to look different. Now, realistically, you can sort of say, I'm going to approximate this with just spikes in each of these places, but it's hairy business. So in any event, what I decided to do is I decided to come up with a model of something simple enough that I could do it real time and play with the parameters. And I partially did this. Originally, there was a paper fairly recent, I think 2010 or something, where they came up with a conversion from what they called red, yellow, blue to RGB color space. And I tried their model, and I didn't like their model, strangely enough. In fact, what was dreadful is that they actually compared their results to some of the other papers where people have actually gone out and measured things and printed out swatches and whatnot. And they showed these pictures of how great their model actually matched these real substances, but it didn't work well for me. So this is the model I ended up using, and this was just me playing around with parameters. And you'll notice there's some powers of 2 in there, and that was that's the model I ended up with. And then I added in one additional thing, which is with my experience with actual substances, you typically, just like with the with the traditional printing, you actually want to add in black, and black pigment is really easy to make, and black pigment just bleeds into everything. And so I added a component for a black pigment. So what I do is I keep track of 4 planes of how much pigment is on the page, and then of each of these 4 types, and then do a conversion on the fly to RGB to get the result. And let me pop out to the actual tool. So here's the actual painting tool, and this gives me what I was really looking for, which is if I have my red and I have my yellow, that I get my orange, sure, but more importantly, there's a lovely green there in between. And that was surprisingly hard to get. And there's a kind of a weird trade-off, because if you, as you tune the parameters, the more you make the green sort of, for simple models, the more luminous you make the green, the more muted the purple is, and vice versa. And so there's this kind of goofy trade-off. And I'm not 100% happy with these, these sorts of parameters, but that's, this was about as good as I could get it. I can kind of see, having played around with this, and then I have the sort of finger tool where I can come over and smudge it together and whatnot. I can kind of see why people would actually dabble in doing measurement, because it is strange how different your expectations are from how things actually respond when you do simple models. All right, now swinging back in the other direction. So I'm making all these entries, and I want to be able to aggregate them together and do interesting things with them. So I throw in I yet again find myself wanting a 4th interpreter written in JavaScript and being disinclined to import someone else as I throw together something else that's been noodling around in my head. So JavaScript has this feature it's acquired recently called promises. This is just, in one sense, it's just sugar around things you can already do with closures, but it's actually optimized in some of the browsers so that it doesn't, like, in normal circumstances, there's inefficiencies with how you would do promises, and there's also the potential that you sort of bleed memory until the promise chain is completely gone, which if the promise chain is never completely gone, then you'll just bleed memory. So having it in the browser is nice in all kinds of happy ways. And so the idea is that rather than just convert straight to JavaScript code that has to run and then relinquish control to the event loop, you can chain together these promises. And the idea is that you promise to do something, and then you may asynchronously do it later, and then you resume some closure. And so for this particular 4th, I expose JavaScript types. I expose a bunch of words that are sort of idiomatic to JavaScript, so you can manipulate the JavaScript types. And then I just scan the entries in my database of stuff for escaped code sequences. And the escape character I settled on for the moment, for reasons that elude me at the moment, is tilde, which is a strange escape character. But so all the lines marked with a tilde are treated as code. And I used because I was trying to keep this incredibly simple, I used a kind of color forth-like tagging where, not color in the sense of color, but in the sense that the defining words are marked with a colon at the end, the compiled words are unadorned, and then words with a tick are marked, are treated as a tick, and then they put a compile token on the stack. And the key thing is that because I got this hodgepodge of entries, I defer evaluating or doing the compile until I've gathered up everything. And so you can define things out of order. And then I go through, and because I also don't want to have a single entry point, the rule is basically certain prefixes get run in certain contexts. Well, as I said before, right? Colon's defining word, tick is an execution token. Oh, and there's a few others. I made a concession of actually parsing out strings because JavaScript is laden with strings, and building on that, there's a prefix for embedding inline JavaScript, so I can define all the words very quickly in the language. So the core of it is a very tiny little piece of code, and there's a bunch of embedded JavaScript. And then the other goofy thing that I did, I'm still not sure I'm happy, is anything that's unknown just gets treated like, I will eval this as a JavaScript value to push on the stack. So that gives me constants and other values. So this means that I end up having to have flow control that manipulates execution tokens. So I'm having to break apart any kind of flow control. I have to break out to a separate word, and I'll show you what that looks like in a minute. But I can define words in line, and because they're all promises, I'm able to chain them together even across callbacks. So that they can be essentially sequential even in the context. So you end up not having a semicolon, right? So to-do can just be over, that sort of thing. So it ends up looking somewhat ordinary, but somewhat strange. Oh yeah, here's things about JavaScript promises. Lets you do things asynchronously in a chain. And the idea is it looks more like blocking. This is sort of a JavaScriptism for doing more linear code. So the idea is you can wrap up some asynchronous thing where you set up some handler that's going to go send a message to a server and respond to you at a later date to have a resolve and reject method. And then you get back a promise. And then when you have a promise, you can say, here's this, wait for this promise to happen, then do this thing, then potentially catch any errors. But you can chain them together. So you can say, well, do something, promise to do something, then wait for it to happen, then promise something else and wait for it to happen, and so on and so on. So you chain them together to get back sequential code, even in a context where you might be waiting for a web server in between, or you might be waiting for other events in between.
What is return? When you say return, what are you returning?
So you're returning a promise, and actually one of the critical properties of promises is that in these embedded functions and the then clauses, if you return another promise, that promise will get evaluated first before the next promise in the chain.
Okay, so the question is, just for
Yes.
everybody else, are you returning promise one, or are you returning something inside the then that does something?
You're returning the aggregate promise of all of these things chained together.
Okay.
Yeah, and that's, yeah, so this is all one big, yeah. And this is a certain, this lends itself to a certain style of programming.
But the other thing is, when you return something, you don't actually know which then, the then thing hasn't been executed yet when you return the thing.
Yes,
So you're returning a promise.
yes.
You don't know what the fuck it is, but you know what it is.
So this lets me do this lets me add aggregation to the tool. So I can do what I call sweeping. I gather information from the entries, and then I can try to summarize interesting things I found with alerts, and then I have a little search prompt at the bottom, and I, rather than just have the search prompt do one thing, my thought was, well, I'll have the search prompt be just one more input to the kinds of alerts and the kinds of stuff that will come up when you are sweeping through these entries and executing whatever code you happen to find in these entries. And the way to do this is any word that starts with start will get run before the sweep happens as the sort of a prefix. So there's an initial sweep that gathers up all the code that's been marked. Then everything that starts with start is run, so you can have several different things being gathered as you go through and you initialize them. For each entry, all the words starting with each will get executed, so that gives you the chance to do something per entry. And then at the end, there's a finish operation that lets you do something at the end after you've done the sweep. So for example, you could tally up, all the entries that have a certain property, look for all the, the pending to-dos, initialize the place you're going to keep them, sweep through each entry, gathering that up, and then when you're finished, issue an alert, perhaps, that something is pending. So there's various inputs to this. There's the query in the query box. There's the content of each entry. There's its modified date. The images associated. I should mention, by the way, the images are stored as, well, actually, no, I'm looking, that's off on a tangent. And then the outputs are a bunch of alerts, and then the ordering of the entries to display. And so the idea is that you could both implement search this way, but you could, and more nuanced search, but you could also offer particular helpful orderings based on what was searched for. So you can imagine adding a command that does something interesting with the ordering. So what's my status? I support distributed entry on a number of devices. I'm going to actually show that here in a second. I support the pastels, which I put probably far more work into than I should have, because of course, as you can see, that has almost nothing to do with the organizational goals. And the core pieces of promise forth are there. You can use it offline, but here's the one little bit I haven't actually sorted out. If you start the app, go offline, you're fine. However, things that are yet to be done, you can't load offline. I haven't set up app cache the right way so that if I've done things correctly, and I mean to do that, but just haven't gotten to it, I should be able to go to the page and it'll fall back to a cached copy, even in the case where I'm offline at the point that I started it. I don't handle dates well. I mean, in fact, one of the whole goals of this might be to be able to say, hey, I should do this within a week, and be able to actually have that mean something, and be able to scan for an alert that does that. I have some ideas about how to do that, but I haven't executed on those ideas. And I have only just begun dabbling in generating reports. I'll show you this very simple ones that I have, but they're really not much to brag about. And then the other thing I learned very recently is that there's a way to do web-based notifications so that the page could actually issue an alert on the phone. What's nice about that is it could alert me on the watch. So, yeah, so anyways. And I might get back to the encryption. And the other thing I'm actually a little bit worried about is the approach that I've taken doesn't particularly have properties that lead me to believe that it would scale very well. And that may not matter because I'm envisioning this as a sort of a personal database. But as I discovered, it's like, well, I've already accumulated 10 megabytes of images and some amount of text. And I'm a little concerned that this sort of let me sweep through the universe all the time, everywhere kind of approach may fall over at some point. So I need to think about what are some graceful fallbacks. Do I maybe not keep all the images locally all the time, or do I keep a lower res version, or that sort of thing? Most of the problem is the images. So there's that. But let's see. Oh, and then I need to actually use it enough to really, I've used it some, but I've used it intermittently, strangely enough. So now I'm going to actually go and demo the thing. The very first thing, of course, I did was make a haiku appropriate to the name iamically, right? So alternating pulse, five up and 5 down, right? Anyways, let me go switch over to the app. So I'm going to show 2 different views of the app. So this is what the app looks like and you can see sitting here, I was doodling. So the most by default, it's showing things in latest thing or most recent thing first, and the notion is just that there's this scrolling panel of here are the things that I've entered, and various entries on different topics. I can search. So, for instance, if I wanted to, I want to look about something with Locke's, system, I took some notes on how Locke's indexing system worked, or I want to look for pictures of a cherry or something. I can go look for that sort of thing. But there's this little icon in the corner. This shows the login state. This is something I'm not entirely happy with. It changes to various icons to indicate, like, that you need to log in. By the way, this is all sort of something locked down to just me at the moment. I haven't made it sort of generally available. And I would like to reveal more information about have we synced everything, how close to synced are we, that sort of thing. Because right now I'm always like, did it sync? If I turn it off now, am I like preventing it from, because I get into this thing of, let's say the server is, and then I use this iambic icon here throughout as the indicator to edit things. So when you say click on an entry, you can edit it, and it comes up to edit the entry, and then or you can create a new entry. So and by default, you got just the text, here today at SVFIG. And if you tap again, you create the entry, and then it shows up, and it's being synced in the background. If I go in and edit it again, so down here currently I have this set of drawing tools, and I'm not happy with these either. I wanted to have a minimal set, and in fact I'll show this in a moment, but this set is actually picked to be this small partially because it fits nicely on the phone. So if you tap on one of these, up comes the canvas to draw. And I'm storing both the individual planes of pigment, but then I'm also storing a snapshot of the image so that I can quickly bring that up. And so I've got, you know, the thick brushes for the pigment, and I actually want these to be, I'm intending to make these stronger brushes. And then the dark pigment, I actually originally played with, when you do pastels, normally you, it's actually typically, pigment is funny business, and it sticks very much to the paper. And so it's very hard to actually erase anything all the way down to white. And so you typically will also have white or lighter shaded pigments. So originally I actually played with a 5-channel model where I had white pigment as well. But eventually I discovered that it wasn't adding much benefit, because in a world where you can really erase down to nothing, it's simpler to just have the four channels. And so then at that point you can tap here to edit, to retain it, or X to drop it away. Now the alerts, there's a bunch of different things. Let me do, well, the simple one I put, so one of them in here, the search is actually not built into the application. If I look for search, this entry here with the tildes in front is actually implementing exact search. And so it's for each entry, it's checking to see if there's an exact match, and if so, it's adding it to a set of entries to show. And so that's how search is actually done. I mean to improve that in all sorts of ways. But I have another word here, info, that I put a little bit of energy into. This one is actually scanning through all of the entries and producing some aggregate information, like how many entries, how much text there is, how many bytes they are in total. And so that was just something that I was able to insert and add and have it aggregate that. But for example, you could imagine let's say we made let's say we go back to our SVFIG entry. If at finish, we could do something like hello, and we could say, hello SVFIG, and then dot actually generates rather than printing a number, it prints any arbitrary value, and it prints it to an alert. So if we now save that, whoa, we get an error because I did something wrong, because I didn't put the colon in front, and that actually turns into an alert that you'll notice at the top. And so now there's this perpetual alert at the top for printing that content. And in the same way, I could create additional alerts sort of on the fly as I think of something that I would like to show and aggregate. And my hope is these alerts are sort of there for whatever duration you've specified, but I would imagine, it can imagine also a type of alert that's a sort of a one-point thing where you actually trigger an alert like on the watch. So let me quickly show one other thing. There's a lovely feature of Chrome that I had never used before this, because I had never particularly tried to debug an app on the phone. And there's a wonderful feature in Chrome. If you ever are debugging something on the phone, you can attach a phone, and there's this inspect option. If you set everything up correctly in the phone, which is actually not at all hard to do, and then you navigate into, well, actually, it's a little weird. You have to do this goofy little click a bunch of times on something. You can then set up an inspector that's tethered to the device, and you actually get the JavaScript console of the device as it's running, which is behaving weirdly. Come on. Let's try that again. It's probably angry because oh, there it goes. And so you're seeing up there the screen of my phone as I manipulate it. And so in the same way that we were able to go in and oops, I paused in the debugger because I had a breakpoint from my last session, and it remembers that, helpfully. Oops, I want that. Let's continue. And so then you're seeing what's in the phone. There's this gap here because this is where the keyboard is. It doesn't show that. But this is incredibly helpful if you're debugging something on the phone because there's no console otherwise. But it's also nice as a presentation aid because then I can show you all, me editing things on the phone, and I can, this entry out and store that. And then the alert goes away at the top because I've changed it live. And so it just sort of updates these things. And so this general sort of thing is hopefully going to get me to record things, and hopefully, if I can get to it, aggregate the things that I'm interested in and start maybe using this to actually track what I'm doing. And I do have this other general thought that I want to be able to have other trusted applications like my desktop perhaps log summary statistics of like how long did I sit in which directories and what was I doing this week. But baby steps. And are there questions?
Well, you need like a application log for that.
Yes.
Because there's ones like for Windows-based systems called Manic Time.
Huh.
Which will track every application you access, how
Uh-huh.
you used it, aggregate it across, you know.
I should look into this, although I'm sure
It's pretty insidious. It's almost like a keylogger.
well, that's kind of almost what I was thinking for. You're thinking of going for, but other questions? Okay. Yes.
You know, in concept, it's very similar to everything.
Yes, there is a certain resemblance. To be honest, one of the things I struggled with this is this question of how personal is this sort of information, and do I feel comfortable trusting a server? Do I feel comfortable trusting a server that's not my server? Do I, what's the boundary? And that's actually indeed. Yes.
Still somebody asks for the information.
I admit that having ended up at this sort of an endpoint, I'm not sure, had I explored the field of options more, maybe I would have found a tool that would have been appropriate. Although, where am I going to find the tool that lets me put in little bits of forth code and change it around on the fly?
Wanted to mention that Thunderbird, the email ability, has a task list calendar.
Oh, next,
Okay.